So welcome to this lecture of digital system design with PLDs and FPGA. Last 8 lectures we had a look at the advanced digital design. We started with an overview of the field or a revision of the field. Then I gave a brief overview of the current state of the art, the basic what is happening in the field. Then we started with synchronous sequential circuit. We have started with the synchronous counter, its structure, how to design it, timing analysis. Then we got on to the design itself. We have seen the hierarchical design of a CPU. We have seen what is data path, what is a controller, how to hierarchically design the data path, and using CPU as an example we have seen the behavior of the controller of finite state machine, what is the structure of it. Then we have seen timing analysis of it and how to design a control algorithm and a finite state machine using state diagram. And we have wound up the whole process with a case study, somewhat realistic real life case study of a data acquisition system. We started with the spec and went through all the way like the partition, data path design, controller design, how to implement the state diagram, the next state logic, output logic, and all the way down, and what is the part of the kind of the designer main part, and what are the tools plus designer and so on. But now we have some portion left in the advanced digital design, but before proceeding I thought it is better we look at this hardware description language, so that when now onwards when we go with the digital design or anything PLDs or FPGA, wherever it is appropriate we can put the connected VHDL or the hardware description language. That is a basic idea, that is why we go. So now for quite a few lectures we will have the VHDL lectures, where my plan is to at least complete the combination circuit description of models and sequential circuit, test benches, and some demonstration using the tools available, free tools available, how to write the code, how to synthesize, how to simulate, and so on. So let us turn to the slide of this VHDL. Okay. So let us look at the slide. Now the VHDL, the full form of the VHDL is VHSIC hardware description language. That means the very high speed integrated circuit hardware description language. It has started in 1970s and 80s by Department of Defense USA. For maybe I will give a brief on the context, so that sometime the context make things clear, you do not grumble or complain why certain things are like that. And it is an IEEE standard, IEEE 1076.3. there are various years, 93, 97, 2012, 2002 and all that. I do not exactly remember, but then these are the various versions of the VHDL. Essentially it started with some kind of limitation of the earlier design methodology, which was using something called schematic capture. Okay. So I do not know whether you are familiar with the schematic capture, but I will show a slide which is taken from the internet of some kind of hardware, digital, mainly digital hardware, but then you see this is kind of some flip flops are there, some muxes are there, inverters are there and all that. A schematic would always involve some symbol of the IC you are using, or the gate or the flip flop. Many a times in terms of the ICs you are using, suppose this is a flip flop which is written IC3B. So and there are pin numbers and it shows how it is interconnected. Okay, that was the earlier days, that was starting point of a design. you put, like you want an inverter, you put the inverter symbol which you mark, which is a part of the IC. Maybe there are 4 inverters in an IC, so or 6 inverters, then it will be IC 1A, 1B, 1C, 1D, 1E, like that the numbering goes. And the pin numbers, you can see that this is the output is 15 pin number, 14 pin number and all that. And people would put symbols and interconnect with the wires, okay. So that was basically the schematic capture. And when one design a printed circuit board, there will be an associated package with it, okay. If it is in the standard library, the package will be part of the library. If the user creates, he has to create what is a package. Maybe old times it was many a times dual inline package. So this was to be precisely created so that the PCB, when one make PCB, it is precise, and the chip goes into the pinholes and the tracks are aligned and so on. But basically essentially a schematic would tell how is the interconnection, or it is called a netlist, okay. Just shows the symbol and the interconnection between the IC, and it does not give you what is the function of the circuit. Many times you have to refer to the data sheet of each IC, try to understand the internal. In simple case gates and all, it will be simple, but if there is a processor, one has to read the data sheet of all the complete processor to understand memory, processor, gates, flip flops, everything need to be understood, and sometimes a design description need to be written saying that this is a particular IC, this is a function of that IC and so on. So that was one big problem, that it just does not convey anything other than kind of connectivity information. That was the first problem with the schematic capture. And the second problem was that there were a lot of schematic capture or the CAD tools, and everybody had many times a proprietary format. That means the CAD tool, if you are using a CAD tool from a vendor A, the file stored in that format may not be openable. You cannot edit using some other tool, okay. That was a big problem. Proprietary standards were followed, and many times this kind of tool did not support something called a black box design. Say go back to our hierarchical design of the CPU, and initially at the level 0 we put a black box and said the clock and reset and read bar, write bar were the inputs, outputs and so on. And then we have partitioned it into a level 1 kind of partition. Still it was black box, that is ALU, registers, program counters. Ultimately when we broke down into known pieces, it has come to some kind of gates and flip flops or some known blocks. So this was one difficulty with the schematic. A hierarchical design was not possible, or top down approach was not possible in this thing. So this tells you that if you had to design a finite state machine, now when we described the finite state machine, we said you could kind of describe that in hardware description language, and the tool will make the next state logic and output logic. This was not possible with schematic capture. You need to draw the state diagram, you need to make the truth table, minimize it, and then implement those minimized equations using the gates and flip flops and so on. So this was kind of external, you work externally and bring the design into the schematic capture. And they also supported some kind of simulation, because there is a flip flop. If the model of the flip flop was available, then you could simulate the whole circuit. I mean, model of all the chips used are available, then using some kind of simulator the behavior of this could be kind of simulated. But again these were proprietary, like the vendor A will give some models, but that was not compatible with the other tools and so on. There were, it's not that it is completely proprietary, there were standards for the CAD file exchanges, the schematic exchanges and the simulation models and so on. But not everyone was following, and there were problems, issues with it, and there was the huge problem was that these were binary files. If there is one bit goes wrong, everything is corrupted, and so there were the problems with the schematic capture. Now the Department of Defense had a lot of vendors making big systems. I mean, they have huge rack of cards comprising a system. Maybe each subsystem was designed by a separate vendor, and they all use different tools, and to put it together and to understand, to kind of coordinate the whole activity was a big problem. That is why this particular standard came up, and they thought of basically documenting the schematic, that started with documenting. So basically to describe in human readable language, English language, the description of the circuit, that was a basic idea, so that it is portable. Like all the vendors use the same language to describe the circuit, so that one can read and understand. That was a basic idea. So it started with documentation, document it well, describe it unambiguously, so that the human can understand, and it was an open standard, it's human readable, it is portable, and so on. Then later on people thought, anyway we are describing the behavior of subsystems or small circuits using some language, why not use that description to simulate the behavior of the circuit. Still the design was largely done on schematic capture, but then the simulation came second. And ultimately when everybody started using simulation, people started thinking, why not generate the circuit itself from the description. Okay. So these are the three uses of the VHDL language: documentation, simulation, synthesis, which happened at different points in time. So you will see all these features in the language. Okay. So there are documentation features, when you look at the VHDL, people will see that the entity is or architecture, a name is of, and all that, and people often complain saying that what this if and of, and why the computer algorithm need this human readable thing. But you should remember that this was meant for documentation, and anyway you can use standard templates, you can make your own templates or copy paste the old templates and so on. So don't complain that much about it. Is a little bit verbose language, so don't complain about that part of it. And similarly there are, when you come back, there are the syntax for simulation. There are some constructs in the language which is only used for simulation, there is no point in using it for synthesis. Okay. So this should be kept in mind. It is not that all, like anything you write can be synthesized. There are some things meant for synthesis, something meant for simulation, some part of the language is merely meant for documentation. So don't complain too much. And the language support hierarchical design. You can do the top down design with a black box, absolutely no issue. You can do bottom up or whatever, and much to the convenience, there are higher level constructs. You can describe the behavior not just Boolean equations, but you can use higher level constructs like if then, case when, loops. So it kind of give a power to describe the language at many levels, at a very detailed level, abstract level, and as we go along we will see what is how we can efficiently use this construct to describe, and what are the best scenarios to use certain constructs and so on. And it supports library based design. That means that you can put, suppose you have designed a counter, a generic counter, you can put that in a library, and later on you don't have to redesign that. So anything which is modular, generic, can be put in the library. Similarly various operators, various functions, procedures, everything can be put in the library, so that can be reused. So it's a great help. You are in an organization, in a particular business, and you're making designs over the years. So you can have a good library of the various modules, subsystems, components you are using, and so that when a new design need to be made you can quickly make it using already well designed components, interconnect them or modify them quickly and put it together. So that is a big advantage. And one lacune or or a feature of the VHDL is that it is strict type checking. That means that data type is strict. You suppose you declare something called bit, okay. Bit is something takes 1 and 0, and there is another kind of data type called standard logic, okay. We will see that, but that also support 1 and 0 and many more things. But in VHDL, suppose there is a signal which is of data type bit, this cannot be assigned to the something of data type standard logic, okay. This is looks like a restriction, but it is a very good thing, because if you do not know what you are doing, because you are interconnecting various signals, and if you are not careful, like you declared something as an integer of some range, and there is some kind of bus which is 8 bit, and you try to connect this integer to that kind of bus, 8 bit bus, maybe that your range of integers is more than 8 bit, and then there is a confusion, like you end up with 12 bits, and how to connect this 12 bits to 8 bits, and if the tool decide that least significant bits will be connected, then you are in trouble. So that is why the strict type checking is enforced. It is a good thing, because we are making hardware not to make mistake. The VHDL enforces strict type checking, and there are, like, it is not that you cannot assign a bit to a standard logic, you have to forcefully convert the data type, then you are aware of it, and then you will take caution, that is why it is provided. So let us move on to the slide, and let us look at the main design unit of the VHDL. So the VHDL design or any block has two parts. When you describe, it has two parts. Any component has an entity which is nothing but the interface specification, and the architecture which is functionality, okay. This, and we will take an example of orbit comparator. This part is taken basically from the reference book Kevin Cahill, at least this starting part is taken from there. So say you look at an equality comparator, so you have A and B which are 4 bit, and there is a single bit signal called equal. When the numerical value of A is exactly equal to B, that means if it is say 1010 and B is 1010, this will be 1, that is the meaning of it. So entity means a name for the block, some name, what are its input port, okay. So you say input port is A and B which is 4 bit, and what is the data type, is it bit or standard logic vector, and so on, okay. So, and similarly, what is the output, how many bits are there, is it a single bit or multi bit, and what is the data type. So that comprises the entity. So give a name for the block, what are the inputs, what are the outputs. So you have to clearly say what is the name, whether it is input, output, and so on, and what is the data type. Now comes architecture. Having defined the entity, you define what is inside. The architecture is nothing but the functionality. So you have to define what is the function of this circuit in terms of the input and output. That means you somehow you say that equals will be 1 if A is equal to B. In some, there are many ways of describing it, but that is the functionality. So you describe the functionality of this block equality comparator in terms of the input and output, okay. So you say output, how the output is assigned from the input, that is the basic crux of the VHDL. Entity and architecture. Entity means the name, input output, the basic the data types, and the architecture means function in terms of the input output. And you know the circuit, when you come to the basic implementation, we need to have each bit, suppose if you have a A3, A2, A1, A0, B3, B2, B1, B0, you can see that for these number to be equal, A3 should be equal to B3, A2 should be equal to B2 and so on. So we use an exclusive NOR gate because exclusive OR gate has 0 1 and 1 0 as 1, but here you have 0 0 and 1 1 as 1. So unless all these are equal, this won't be 1, and if all these bits are 1, then we have this AND gate is making it 1. So you know the circuit for exclusive OR gates exclusive NOR gates, and one AND gate is a function. So that is the VHDL way of describe main kind of component kind of sub description, entity and architecture. So let us look at this equality comparator VHDL code straight away and try to kind of see how to write a VHDL code and what are the basic components and so on. So say when you, like I have written here 2 dashes in 4-bit equality comparator, that means this is a comment. Okay, if you start a dash anywhere, you could I could put 2 dash here and write something. So anything after the dash is a comment, and you know that there is no way to kind of make it nest with multiple lines. Not a big problem. Earlier when people used to use the keyboard, that was a big problem. Now suppose you have 10 lines to comment it, if you have to put everywhere, it's a big problem. Nowadays with the GUI it's very easy, you select everything and click on an icon, then everything become commented. So this is a comment character only for a line, you cannot nest it. Okay, and the next thing is interesting, it say okay, now I have shown the code in 2 colors, basically in green and blue, and whatever is written in the green color is a VHDL keyword and rest is what we are writing. Okay, so that is to make out. So like library is a keyword of the VHDL, use is a keyword of the VHDL and so on. Okay, so here we are saying we are going to use library IEEE, that there are IEEE standard libraries. So we are saying that we are going to, for this entity and architecture, we are going to use library IEEE. So when you declare that this IEEE libraries are visible only to this entity and this architecture. Suppose in the same file you write another entity and architecture, you have to, and you need to use a library, then you have to write again library before the entity and architecture, and just writing the library, it makes a library visible to the code but not the packages. Library has lot of packages within it, so it's a hierarchy of library. So you have library, you have packages, and within the packages you have components, functions, procedure, data type and so on. Okay, so that's hierarchy, and we are going to say that we are going to use a particular package within this library called standard logic, standard underscore logic underscore 1164.all. Okay, so we are going to use this particular package for this entity and architecture, that's the meaning of this. And now onwards we are going to use the standard logic library. The reason is that if you look at the VHDL, inbuilt data type is bit. Okay, as far as the logic is concerned, and it supports only 2 values, 0 and 1, and this is a great limitation, and for digital design we just cannot do with only 0 and 1, we need many other things. At least you know that we have tri-state gate which we use, and we want to use at least an Z describe saying that some output need to be tri-stated. So that is described in a standard underscore logic, and that's a kind of data type which is used, which is available in this particular library and package. So that's why we use this. So it supports the data types like 0 1 values like 0 1 Z, and there is many times in minimization we use don't care, so it support don't care and all that, many more we will see what are the values in this standard logic data type, but for the time being understand that it will at least support a Z which is represent the tri-state, which is very much required for the design. So now onwards all the code we will not get into bit, we will use the data type standard logic, that is what it shows. Now this comes the entity description. So the keyword is entity, give some name, it does not matter, and this is what I said is a kind of for documentation, and you say end this particular name eqcomp, okay. So that is a body of the entity. So you start with the keyword entity, a name is, and end that name, then that is kind of that is the body of the entity, and within that we have to describe the inputs and outputs, and the keyword used for that is port. You open the port with a parenthesis left and right and semicolon. You can see that all the kind of syntax is terminated by semicolon. So if you describe something, a complete entity, then you put a semicolon, complete port, then you put a semicolon. Everything, every statement, every kind of the body is terminated by a semicolon. Now you see this is the input specification and this is the output specification. So we have two types of inputs, two inputs A comma B. So if it is of the same size, same data type, we use it in the same line, say here A comma B, then you put a colon, this is the name. Now we say what is the direction of the port, it is an in, means it is an input, and standard underscore logic underscore vector 3 down to 0, that means that the A is a 4-bit vector which is A of 3, A bracket 3 like we have seen here, A of 3, A of 2, A of 1, A of 0. Similarly B of 3, B of 2, B of 1, B of 0, okay. That is the meaning of it. The moment you say standard logic vector 3 down to 0, that means it is A of 3, A of 2, A of 1, A of 0. There is another syntax, you can say instead of 3 down to 0 you can say 0 to 3. It is possible to write like that, and there is a difference. We will soon say what is the difference, and let us come to this equals, which is a name, and the mode of the or the direction is out, and the data type is standard logic, okay. So when you describe a port you have to give a name, you have to tell the direction, you have to tell the data type, and now when you say there has to be clarity with this kind of direction of the port. So when you say in, it means that it is an input, okay. It cannot be treated as an output, that means that when you write some assignment, like here we are writing the assignment equals get 1 when A equal to B. So A and B are the inputs. In any assignment the input can come only at the right hand side of the assignment, okay. That should be kept in mind. When you have something declared as a direction in, it can come only on the right hand side of the assignment, and there is similarly there is out, and out means it is an output port, something drives, there is an some kind of gate or flip flop, its output is driving a signal which is outside, and when you declare something as out like equals, that should come on the left hand side only. You cannot write something like Z gets 1 when equals equal to something. Now you cannot write on the right hand side, okay, but that could be a restriction, and you look at this kind of thing, like we have many times an output, a tap is taken from the output and used as an input to some circuit inside. This is quite common, you have something coming like some gate is driving an output, but that output is going to the output pin, also it is used as an input to the further circuit within this block, okay. But by definition if you use a out, such a thing cannot happen with the VHDL. So there is a roundabout, there is a kind of way out, that is to declare this output as buffer, like you say equals is buffer, standard logic. But this has a problem, because as a standalone it is okay, but when you have multiple components buffer, it cannot be connected together. There is an issue with the buffer. So I don't think that you should, or we will not be using this particular direction of the output signal at all. And what we are going to do is that there are internal signal, you can use signal. So what we are going to do is that we will normally in our codes we will declare a signal here which can definitely connect to some output and can connect to some input, and ultimately this signal we can assign it to some pin. That is what we are going to do in our code. So literally forget about this particular direction of the port buffer. Now there is one other direction specification which is nothing but in out or an IO. So now that is not a same as buffer. In the case of buffer it is still an output, the pin is an output, but there is a tapping which is used internally, okay. But when you say something is in out, it literally means sometime there is definitely a tri-state gate, and when the enable is 1, this circuit will drive the circuit which is outside, okay. And when it is cut off, when it is not disabled, this part is inactive, there is nothing, it is tri-stated, and this can be used as an input pin. That means literally something can drive the pin, okay. So there is a difference between this structure and this, and you should not use in out for out or buffer, okay. And I have seen sometime people use out and something goes wrong, and they somehow find that if you write in out that can be circumvented because of some kind of simulator difficulties. Maybe at the appropriate time I will tell. People tend to use in out where in out is not meant to be used, okay. So that should not happen. You should not use in out in place of buffer. That in out is used only when a pin is used as both as output and input, and necessarily there has to be a tri-state gate, without which there is no way to use an IO pin. Now that is the kind of various direction in out, buffer and in out, and as I said forget about buffer, we will use the wires, I will show at the appropriate time. And standard logic vector is a repetition of the standard logic, like this is a 4-bit standard logic is a standard logic vector, and as I said you could write 3 down to 0 or 0 to 3, okay. There is a difference. When you write 3 down to 0, the most significant bit is 3 and least significant bit is 0. When you write 0 to 3, the most significant bit is the 0, that means whichever comes on the left hand side, and the least significant bit is the 3 which is on the right hand side. So the rule is simple, whatever you write on the left hand side is the most significant bit, and whatever you write on the right hand side is the least significant bit. Now you might ask what is the big deal, what does it matter, okay. It matters if you have studied a kind of the processors from the Intel. Actually this has some history behind. The Intel processors used to treat, suppose you have a data bus which is going from 16-bit data bus, the D15 was treated, say the data 15 was treated as the most significant bit, and D0 was treated as the least significant bit, and this was called little endian. That means the small number will end is it at the end part, and then the Motorola which was a kind of a competitor to Intel, when they came out with this processor, subsequently that has become Freescale, but when they came out the numbering was kind of opposite. The say D15 was LSP and D0 was a MSP, okay. Now you can imagine so this is something to do with this 3 down to 0 or 0 to 3 has something to do with the kind of the bit order and the byte order and so on. So if you are using little endian, then you should use terminology like 15 down to 0. If you are using big endian, then you should use 0 to 3. So you may even end up with you are designing a chip, on one side you are connecting to some other chip from another vendor which has a bus in little endian order, and the second side has a bus which is in the big endian order. Then you should appropriately kind of define this properly, otherwise things can go wrong. So you should keep that in mind. It's not that it's not your convenience, but if you are designing a complete chip of your own which is not to be interconnected anywhere, then you can choose what you want to do, like whether you adopt a little endian or big endian kind of style for your multi-bit signals, that has to be decided. So that is all about the entity. So we have looked in detail what is the entity, what is a port, what are the directions, little endian, big endian in the case of multi-bit and so on. Now comes the functionality which is defined as architecture. So you say architecture, which is a keyword, give some name arc underscore eqcom, that is my style of doing it, of this particular entity. Say whatever the entity name is written here. So this is the kind of link between the entity and architecture. You say architecture, a name of which name you have to say is, okay. Now you say begin, that is where you describe the functionality, okay. And before that, before the begin, you could declare many things, you could declare components, you can define functions, procedure and so on, okay. So we will see what could be done before that, and when you write say the statement, we will see what are the statements and so on. Say this is an output signal and this is an assignment operator which is exactly similar to less than or equal to. The VHDL also use the same for the less than or equal to. So depending on the context the meaning of that is derived. So 1 is written with the quotes, left quote and right quote, because in the library, in the standard logic library, the values are defined with the quotes like 1 with the left quote and right quote when A equal to B, else it is 0, okay. So equals get 1 when A equal to B, else it gets 0, okay, very simple. The description is over and you say end this architecture, whatever is the name. So that architecture is over. So that is the code in a nutshell. You have a comment, you have a library, you have a use package kind of construct, you have an entity with port, mainly within the entity is a port, direction, the data type, the multi-bit declaration, then the architecture. Before the begin there is a declaration. In the statement region you write various statements, then the description is over, okay. So that is in a nutshell kind of the basic VHDL code. So and you can use various keywords, various names, and let us move on to the slide. Summarize whatever I have said. So I have said comments start with anywhere on the line, and library as an hierarchy library, packages, and it contains components, functions, procedures, various data objects, data types and things like that. Then you have different mode or direction, you have in out and buffer, and we said this has very limited usage, and in out and out is different or buffer is different. Then we have down to and to, so you have to worry about little endian, big endian, bit order, byte order and things like that. And when you define some name, you can use alphabets, you can use numbers, you can use underscore, and it is not case sensitive. First character should be an alphabet, the last character should not be underscore, and you should not have 2 underscore in succession. And I don't remember the exact number of characters you can use for the, maybe it is 32 characters you can use, you can check with the standard because the standards keep changing. but for practical purposes your normal names you can give quite a long names, there should not be problem, but better to check with the VHDL latest standard and the tool compatibility, what the tool support. Maybe you refer to the VHDL latest standard but the tool support the earlier standard, then you will be in trouble, then you should be careful with that. So that is in summary about the code. So let us move on. The architecture body. So we have said that in an architecture before the begin you can declare many things, there is a lot of things you can declare, that is what is shown here. The architecture has two parts. Before the begin you can declare something, after the begin you can write the statements, you can describe the function. So what all you can declare is that you can declare components. Components are like equality comparator, gates or flip flops or multiplexers, encoders, all that is the components. The type, data type like standard logic, bit, boolean and things like that, and constant like you have a bus width you can decide, define as a constant like size or width. Signal we have described like you want to interconnect kind of two ports or output of some block with an input of another block, then you can use signals. You can also use functions and procedures. For the time being we will keep it aside, but then you can literally define functions and procedure, not declare. You can literally define in the architecture declaration region, which is visible only to the architecture statement region. Okay. So after architecture statement region is where you put all the description in terms of various constructs. So let us turn to the logical operators. So you have all the logical operators, you have AND, NAND, OR, NOR, XOR, XNOR and NOT. But the trouble with the VHDL is that the basic operators within VHDL support only the bit and the boolean. Okay. But as we described in the first slide, we are not going to use the bit because it is restricted by 1 and 0. We are going to use the data type called standard std underscore logic, we call it standard logic. So std underscore logic is called standard logic, and this is but you do not have to worry about the logical operators for this data type, because in this particular package IEEE standard logic 1164 package which we have used in our code, the first example code, this logical operators are overloaded. Overloaded means whatever was written for the bit is rewritten for the standard logic data type. So the moment you declare, you like here the moment you declare use IEEE dot standard underscore logic underscore 1164 dot all means we could use all that and NAND, all that here in the statement region, and the all means everything in it, like that means the entity and architecture following this use construct can use whatever there is within this particular package, that is the meaning of all. So that is the logical operators. Then you have arithmetic operators, you have the plus, you can add, minus, multiplication, integer division, exponentiation, because many a times we work with the power of 2, then you suppose you have a data bus which is 8 bit width, then you know that it can go take values from 0 to 2 raised to 8 minus 1. Okay. So where these kind of exponentiation operators are useful. Then you have a modulo division, kind of modulo remainder, then the absolute value. There is a little confusion with this terminology, like mode is different from the computer science mode. The mode definition is say A mod B is A minus B into N, like suppose you say 13 mod 3, that means you know that it is 13 minus 3 into 4, so which is 12, the highest number you can put before it crosses over, then you get 1. Okay. So if you know that when you do a mod n, the result has to be 0 to n minus 1, but there is an issue with this kind of the expression, because it doesn't work well with the negative values, because you know that the mod n has to map any number to 0 to n minus 1. So that is why this rum operator is given, which is actually this is equivalent to the computer science definition of the mode. A rum b is nothing but a minus the floor of a by b into b. Okay. For positive numbers it makes no difference, because if you say again 13 mod 3, it is 13 minus 13 by 3. Integer division is, sorry, the kind of the real division will yield you 13 by 3 will give you some 4 point something, which is the floor of that is the decimal part is thrown off, the fraction part is thrown off, so you will get 3, and 3 into 4 is 12 and 13 minus 12 is 1, you get it correctly. But if you say minus 13, then you will end up with there is a confusion, but with this formula there is no issue, because minus 13 by 3 you will get minus 3 point something. The floor of it is the lesser number, so which is minus 4 into 3 is minus 16, and you have minus 3 minus minus 16, you get plus 3. Okay, you don't get a 1, but because you are sorry, it is 13 like minus 13 by 4 is 3.4, 4 into 3 12. So this is minus 12, so minus 12 plus 12, and you will get you will end up with a positive number. That is the crux of it. You can work out with an appropriate example, but very important thing to note is that all these operators are defined internally for the data type integer and real. Integer is the integer, as you know, the real is the real numbers or the kind of floating point data type. This internal operators will not work for the standard logic data type, but if you use standard logic unsigned package in the use case, like you say library IEEE and you say use IEEE dot standard logic unsigned dot all, then you can use plus minus multiplication division and all that. Mind you, if you write a code with this with the standard logic, it might work for simulation, it may not synthesize and generate a proper circuit for you. You have to keep that in mind. Everything doesn't work, sometimes you have to write your own low level design for some of these to work, or it will give some rudimentary circuit which is not that we want and things like that. So you have to keep that in mind. And let us come to the relational operators. So relational operators are equal to, greater than, less than or equal to, greater than or equal to, and not equal to. Okay, these are the relational operators. You say when A equal to B or if A less than B and so on, and you see that less than or equal to operator is same as the assignment operator. So depending on the kind of context you use, the tools will infer what is the kind of operator, appropriate operator, and will find it. You don't have to worry. Once again, internally these are defined for integer and real. For standard logic data type, this is overloaded. These operators are overloaded for standard logic function in the package called IEEE.standardlogic_arith. Okay, so in principle, like if you use 3 packages like IEEE standard logic 1164, IEEE standard logic unsigned, and IEEE standard logic arith, you can do many things with the standard operators. At least you can work with the standard logic data type, so keep that in mind. And when it comes to shift operators, you have logical shift, arithmetic shift, and rotate. So you have shift left logical SLL, so that is just simple left shift, shift right logic is symbol right shift, and shift left arithmetic and shift right arithmetic works with the 2's complement numbers. So in 2's complement number you know that the most significant bit represent the MSB or the most significant bit, and that is a sign bit. So for negative numbers it will be 1, and when you extend, suppose you have an 8-bit number with the sign bit as 1, when you convert this into 16-bit, then all the numbers starting from the 9th a number 8-bit to 15-bit has to be 1. So when you do a shift left arithmetic, this sign extension will be automatically taken care. That is the meaning of shift left arithmetic and shift right arithmetic. So if you do some arithmetic using the shift operators, like you know that shifting left is like multiplying by 2, shifting right is like dividing by 2, and if you are working with unsigned integer, then the shift SLL, SRL like logical shift works. But if you use arithmetic, like if you use kind of signed integers, then you have to essentially do the shift left arithmetic and shift right arithmetic to preserve the sign, otherwise things will go wrong. And you can work out, you take a 4-bit number, work out the negative numbers, you work out if you extend it into 8-bit, make sure that you get the same value with the sign extension. That should convince you, and that gives you little clear understanding of the 2's complement numbers. You can work with even the decimal numbers and how this whole game works. You must have studied, but then that brings clarity. And once again the shift left arithmetic and shift left logical and arithmetic, all these are defined for the bit and the boolean data type. For the standard logic data type, this is overloaded in the standard logic arith package. So that is what I said, you use these 3 packages, most things will work. Standard logic 1164 unsigned and arith, and you have an operator called aggregate operator. Essentially it is shown here. Suppose you have a signal like standard logic signal with A, B, C, these are single bit signal. Okay, now I am using bit, do not confuse, bit I mean the real bit of the digital system, not the bit data type of the VHDL. Okay, so here we are trying to make it combine ABC into a 3-bit kind of bus. So you have a signal, signal is a keyword, this is a name which is of type standard logic vector 2 down to 0. That means there is temp2, temp1, temp0. Now we say temp is nothing but assigned in the brackets you say A comma B comma C. That means temp2 is A, temp1 is B, temp0 is C. So this is called aggregate operator. So you can aggregate individual signals which can be single bit, multi-bit to a bus, but the restriction is that these elements, individual elements should be of the same data type and should be same size. It is not that A can be 3-bit, B can be 2-bit and this is single bit. It has to be either single bit, 2-bit, 3-bit together. But even better flexible operator is a kind of concatenation operator which will work for the same data type for different size. Say you can see here we are declaring a data type, new data type, which is the keyword is type. Byte is array, array is a keyword, it is an array of single bits, that is the meaning of it. 7 down to 0 of bit, okay, bit is the byte is nothing but an array of 8-bit array of bit is the meaning of it. And we say signal count is a byte, and we say now the byte is an 8-bit kind of signal, we say count gets 0, 1, 0 and 0, 0, 1, 0. So this is a 3-bit kind of signal and this is a 5-bit signal which is combined it. So this AND is much more flexible concatenation operator, the type has to be same but you can join things together. It is very useful in digital design. You have some kind of some parts of the bus come from different places which is combined together to make a bigger bus and things like that. So that is very useful, these operators, and there is a precedence of the operators. So you have the highest precedence is 6. As you go down 6, 5, 4, 3, 2, 1, 1 has the lowest precedence. So you have miscellaneous operators are highest precedence, then multiplying, addition, shift, relational and logical operators, and NOT operator has precedence 6. And when you write the same precedence operator from left to right, it is evaluated left to right, but it is very difficult to remember all these. I suggest you remember the kind of use the brackets possible. It is good for understanding. Even if you write the code, somebody read, it's very easy to understand. So maybe we will stop here today's lecture. So we started with the VHDL, how did it kind of evolve, what was the basic context. The Department of Defense has trouble with the schematic, so it started with documenting, then used for simulation, synthesis. It is human readable, it works with the computer language, support hierarchy, support a higher level construct, library based design and so on. It's an open IEEE standard, so whichever tool doesn't matter, the different tool vendors, everybody uses the same language. And we have seen basically an entity and architecture. Entity is the interface, architecture is a function. Then we have seen an example code. We have looked at the entity, port, the direction, the mode, the data types, bit order, byte order, then architecture, declaration region, statement region, a statement, and various operators. We have seen the logical operators and the particular data type called standard logic, and which are the libraries which is used for the standard logic. Then we have looked at the arithmetic operators. We have found what is the difference between mode and RAM. Then we have looked at the relational operators, 2 special operators called aggregate and concatenation operator. So now in the next class we will see a little bit what is the design tool flow, various kind of different models of description and so on. Okay, so I suggest you, it looks simple to start with, so please go back, brush up, understand it thorough. You can refer to some good books to get a grip on this particular VHDL. There are a lot of good books. As I said earlier, maybe you use some book with synthesis as the emphasis. So that is it. I wind up this lecture. I wish you all the best and thank you.